Okay, so in this video, I'll be solving example 5.2, which is called drag force of wind on a weather balloon. Okay, now this example, I gave a rough breakdown of this and just sort of briefly started it in video number 14. So remember, this example really goes hand in hand with the material in video 14. And so this is a similarity exercise where we're going to talk about how you would use a smaller scale model of the weather balloon and test that to figure out the forces on the larger scale weather balloon. Okay, so our weather balloon example says you're asked to determine the drag force caused by the wind blowing over a weather balloon. The weather balloon has a diameter of 3 meters and has air blowing over it at a speed of 7 meters per second. To calculate the drag force, you decide to build a small scale model and test it in the ACE wind tunnel. So first, calculate the speed you must run your wind tunnel at if you are also using air and your scale model has a diameter of 0.6 meters. And then B, determine the relationship between the force you measure and the force the actual balloon experiences. Okay, so when it says part A there, calculate the speed you must run your wind tunnel at, what it's saying there is must run your wind tunnel at to make sure you have similarity, right? So the only way you get this thing to be meaningful is if you have dynamic similarity. So for part A, as we saw in video number 14, we just have to make sure that the two Reynolds numbers are equal. So instead of prototype, I'm going to call these actual. So I'm going to write out what the actual diameters are and then what the diameter of the model is. And just to make this as relevant as possible, it's oftentimes a little challenging. We don't work with meters per second super often. So just to give us sort of a bearing on that, that's roughly 25 kilometers an hour. Okay, so we go ahead and make sure these two Reynolds numbers are equal. Let's take a look at that. So model one's on the left, actual one's on the right. Both of these things are in air, so the first thing we can do, we already know the densities and the viscosities are going to be equal because those are fluid properties. So let's cancel those off on both sides. We already know those are equal. Okay, now all those are given and we're asked to figure out what the speed we have to run in the wind tunnel to have proper dynamic similarity. So I'll rearrange for Vm, which is the speed the model will experience. Now I'll sub in. Okay, so I'm going to have to set the wind tunnel to run at 35 meters per second so that this little smaller balloon experiences the same drag forces that the large scale balloon does. So that's really interesting to see that, right? Also for reference frame here, so 35 meters per second, that's roughly 126 kilometers an hour. So now we start to see some of the interesting trade-offs here, right? Like, yeah, it's much more convenient in a lot of cases, easier, or you can use a smaller wind tunnel if you use a scaled down model, but you're gonna have to be able to get those speeds up very, very high to make sure you still have equivalent Reynolds numbers. So that's why another reason the ACE wind tunnel is so interesting, right? Because it's so large, sometimes you can use a full scale model, which actually saves some of the cost to the user because sometimes building those small scale models do cost money. We have 3D printing now and lots of ways to reduce the cost, but it's still fairly expensive. As we saw in the videos, is very intricate model building. So that's one of the benefits that the ACE wind tunnel is so large. Now, just as a quick point of reference here, if we did want to, for example, do a quick check on the Mach number, speed of sound in air is roughly 343 meters per second. So our Mach number then is roughly 0.1, so we're only at roughly 10% of the speed of sound. And normally we don't even worry about that until we're at about 0.3 or 0.4, so just as an aside, we're totally fine in terms of compressibility effects here at this speed. Still worth doing a quick check on that in practice just to make sure. So yeah, smaller, a little bit easier to manage, except you're going to need these really high speeds. So that's the trade-off. Now let's go down and look at this plot here for part B. It's important to remember that the force that we measure on this balloon, so we can actually measure the drag force by using little force gauges. When we measure the drag force though, on that smaller balloon, how does that actually relate to the larger balloon? So let's go look at the plot and see why this works first. I'll scroll down here. Okay, so this plot helps us understand a lot about this problem. Firstly, it helps us understand why equal Reynolds numbers will give us the drag force relationship. So if we look at the bottom axis there, we've made sure our Reynolds number is the same. And in this case, it's roughly 1 times 10 to the 6, which is approximately here. So our force parameter, which is actually our drag coefficient, is going to be exactly the same on the small sphere and the big sphere because we've matched the Reynolds number, and there's only one drag coefficient value that matches that Reynolds number, which is shown on the y-axis. So right around there. But now part B wants us to make sure that the forces, whatever forces we're measuring in the wind tunnel, how do those relate to the actual weather balloon? So to do that now, we have to compare the two force parameters. So that looks like this. So we know these two force parameters are going to be equal, so I'll write those. Okay, we're working with the same fluid, so again, the fluid properties is density in this case, so we can cancel those off immediately. So in this case, it's the actual force we want to know, so let's go ahead and simplify for actual force, where actual, again, is the full-size weather balloon. So we can simplify this a little bit here. Now from above, what happened with the Reynolds number was we already made sure that V times D was equal in both cases. Because we were working with the same fluid, that's how it's simplified. So we can cancel those off. We know VA times DA equals VM times DM. And again, feel free to plug in numbers here if you like. So I'll simplify this. So that shows us that whatever drag forces we measure on the balloon in the wind tunnel, those are going to be exactly equal to the forces that the large-scale weather balloon experiences. Okay, and it might be tempting to think that's always true, but what you really want to notice here is that's only true because we use the same fluid. So we used air in the wind tunnel and we had air for the actual case. There is going to be a lot of times where you might use a different fluid. For example, you might have a water system, but you're going to use air in your wind tunnel. Or you could, for example, use some other kind of inert gas like helium, for example. And using these different fluids, you see, they actually might allow you to use slower or quicker speeds. Like, there's a lot of benefits to sort of also playing around with different fluids. And so long as your Reynolds number is equal, you're fine. But in this case, had the density been different in this force expression here, it wouldn't have yielded that FA was going to equal FM. We'd actually have to plug into these two expressions here to figure out how the drag forces relate. Because remember, what's equal is the two parameters. The drag force parameters are equal, not necessarily the drag forces themselves. In this example, they just happen to be equal because the fluid was the same. Okay, so that I think gives us a really sort of solid footing as an example of like exactly what you'd sort of do to build a scale model, how you'd make sure there's dynamic similarity, and how exactly we go about using all these dimensionless parameters that we just came up with. So I think that's a really sort of elegant way to show everything from this section, sort of all in one nice example here. And these are the types of problems that we're going to be focused on when we talk about section 5. Really brings together the power of the dimensional analysis and similitude. Okay, and that's all for this example.